Okay, so in this video we're going to be looking at what's known as the equation of a line, okay, part of the vectors topic. So reading the first bullet point, or first paragraph, says we can describe a line in space if we know what direction the line runs in and we know the coordinates of a point on the line. Now in order to do that we need to make sure we notate it correctly, so we're going to consider a line L which passes through the point A, which has components x1, or coordinates of say x1, y1, z1, and you can see from the diagram it's going along a direction vector u, which we'll say is AI plus BJ plus CK. Now, we're going to let P be any point along that line also, so we know it's going to have an X, Y, and a Z coordinate, but we now can understand how this works. So if I want to go from A to P, then basically I'm travelling along my vector U for some value T, okay, for some distance along at T, okay, T for some scalar, okay. Now, from higher, in fact, actually from National 5, you would see that to work out what A to P is, we get the P vector subtract the A vector, and therefore if I just rearrange that slightly, I end up with my point P equaling, or my vector P equaling the vector A plus the parameter T multiplying my vector U. Okay, so what I've done is I've broken it down underneath in components form. Okay, so I'll give you time, you can pause the video and you can write this down, but it's just splitting each vector into their components, and you can see that my final answer for what that would look like, I can write that down as like three equations. Okay, one equation gives me the x value for the x component, second one for the y component, third for the z component. Now, what this is called, and there's a note underneath which I'll get to write down, this is called parametric form because all equations have a parameter t involved in them. Okay, so that's what's called the parametric equation of a line. If we rearrange each equation for the parameter t, then I get these three fractions, okay, for each component, and because it will always equal the same parameter t, they all equal each other, and that's what's called the symmetric equation form. Okay, so there's two different forms that we'll be using a lot to represent vectors. First one, the second one's being parametric, third one being symmetric. Okay, the first one that we wrote up here, just so I'll put it at the start again, that's just called the vector form, okay, but they don't break it down into the components. So those are the three things that we'll be doing. Okay, so I'm going to let you pause the video now. You can write down what I've just mentioned there, like how I've done there for you. Once you've done that, if you look at the last note, the really important thing is that if any part of the direction vector, which was u in our case, if any part of that is 0, then we must use the parametric form. Okay, we can't use the symmetric form because our direction vectors, the components end up as the denominators and we can't divide by it as 0. Okay, so go back, read over anything before you go into the examples if there's anything unsure of, but we're going to look at 4 examples. They are quite quick to answer, to look at how these work, I should say. So let's look at the first example. So, example 1, we're basically going to write down, and it's asking us for the symmetric form of the equations of the line which passes through the coordinate 1, negative 2, 8, and is parallel to the vector 3i plus 5j plus 11k. Okay, so that's what we've got there. So, that's my point. Okay, that's going through the line. And over here, that's getting me my u vector, the direction vector, which would be 3, 5, and 11. Okay, so that's what's going on there. So back in the notes, that would be the same as my A, B, and C that I had written on my front page. Okay, that's what that's telling me there. So how would that look like in symmetric form? So symmetric form, okay, so what we've got is we've got x minus x1 over A, that equals y minus y1 over B, and that equals z minus z1 over C, and all that would equal the parameter t. Okay, we got that from there. So, what that would look like just with our information, okay, well x1 is the x component of my point that I'm using, so it'll be 1, so it'll be x minus 1, divided by A, which is the x direction along my vector, u, which will be 3, so that's my first fraction there, so that's where the therefore symbol. That will equal, and we do it for the y, so it'll be y minus, okay, our y point was -2, so that'll end up being +2. And then b, the y direction was going 5. Okay, and then z would be z minus 8 over the value 11. And all that would equal the parameter t. Okay, and that's we wrote the equation of that line that would be written in symmetric form. Okay, obviously parallel is really important because it means it's run along the same direction. Okay, so that's the first example done, but it's understanding where your values go, where your numbers go, in this case in a symmetric form. Okay, we're now going to look at a second example that's going to relate back to this example. So again, you can pause the video to catch up, but we'll move on. So, example 2, does the point -2, -7, -3 lie on the line from example 1? Okay, so once we've found that line, does this point lie in it? And like what you've done for many years now, if you want to check if a coordinate lies on an equation or a function, you substitute your values in and you check, does it come out properly, does it work properly? And if any part doesn't, then we know it doesn't work. Okay, so what we're going to do is we're going to substitute into the symmetric equation that we got, which is x. I'm just writing this down again, which is -1 over 3, which equals y plus 2 over 5, and that equals z minus 8 over 11, which all equals some parameter t. So that was the equation that we found from question 1. Okay, from example. So what we're going to do is we're going to substitute our coordinate x, y, and z into these three fractions and check that we get the same value because they should all equal each other. So if I put -2 into the x, it will be -2 minus 1 divided by 3. And if we work that out, that would actually give us the answer -1. Okay. If I then do it for the -7 for the y, then it'll be -7 plus 2 divided by 5, which again would give me the answer -1. And if I did it for the z, that would be -3 minus 8 all divided by 11, which again will give me -1. So each fraction does give me the same value. So therefore, they should have because they all equaled each other. So therefore, since we get the same solution, point -2, -7, -3, y is on the line. Okay, so that's the second example there. So again, feel free to pause the video, copy that down. Okay, but we're going to look at a couple more equations now just to look at some slight differences of what you can be asked. Okay, so example 3. Find the equations of the line passing through 2 points here. Okay, so we've got 2 points, A and B, and we want to find the equation of the line passing through. Now, note, we haven't been told what representation of the line we are allowed, so we can choose any. Okay, I'm going to show you both, but you can choose symmetric or parametric for this question here. We do that. What hopefully you notice. Okay, the two things we need in order to get the equation line is we need the direction. So the first thing I need to do is work out what my direction vector is. So I need the direction, I need the vector that takes me from A to B. That's the first thing I need to work out. Okay, how do I get from point A to point B? That'll give me the direction there. Okay, so then it'll be B minus A. That'll be 3, 4, 5. Subtract 2, 1, 3. Which will give me 1, 3, and 2. Okay, so I'm going to put U at the start of this just to show, keep our notation similar, that's my direction vector there. Now, just to let you know, at Advanced Higher now, your answers may look slightly different to somebody else's working, depending on which coordinate you use to help finish off your line. In this example, I'm just going to use coordinate A, but if I use coordinate B, my answer might look slightly different, but both would be correct if done properly. Okay, but I'm going to use example A. So, since it passes through A,
do we know it passes through?
So, since it passes through A, reading the question again, then again you could have chose B. So if I start off with the symmetric form, okay, so symmetric form, so again, what did that look like? That was x minus x1 over A, and that equals y minus y1 over B, and that equals z minus z1 over C. Okay, and just a reminder where we get each value for. So, made a mistake there, sorry, that should actually be, if I'm using the A value, A coordinate, that's going to be x1, y1, z1. And remember, my u vector is my direction, which is denoted A, B, C. Okay, so I'm just going to sub these numbers in now, so it's going to be x minus 2 all over 1. Okay, and that equals y minus 1 over 3. And that equals z minus 3 all over 2, which would equal some parameter t. Okay, so that's me wrote the equation of the line in symmetric form. Now you might be looking and thinking, well, if you look at the first fraction, we've got something divided by 1, and normally you don't need to write that. And that would be the case in a lot of places. But that 1 is part of the direction vector, so therefore I would keep that there, okay? Because when we try and translate that back into what parametric would be, just to show you what that would look like, then we need to use, okay, so the parametric version for that line, just because the question didn't specify, so we could have picked either. So now that we know the symmetric version, we can actually just rearrange each fraction and actually get what the parametric equations would be. So for the x fraction, okay, well if I times the 1 over, so that's 1 lots of t, and added the 2, I'll get x equals 2 plus t. Okay, so that's me just rearranged that first one there. In fact, do I want to write it that way first? Yeah, I do. Okay, so that's the first one. Y, okay, I would times by 3, so it would be 3 lots of t, but then I would add the 1 over, so it would be positive 1 plus 3 lots of t, and then z times the 2 over, so I've got 2 lots of t, add the 3, I would get z equals 3 plus 2t. So there's the 3 components for the parametric equation there in that form. Okay. The main thing was we didn't have the direction vector there. We had to find that first, and then I could use either point. And if I use point B, my answer would look slightly different values in there, but it would still represent that line. Okay, so you might end up with a different solution to what I did, but if it's done properly, it should be right. Okay, we'll look at one last question, and then I'll be off with the video. So, example 4, find the symmetric form of the equation of the line passing through the point 6, 3, negative 5, but is parallel to the line x over 3 equals y minus 10 over 5 by negative 2 equals z plus 8 over 13. Okay, so this is a little bit like when you were in National 5 and you had to find equations of lines that were parallel to another line, for example, or perpendicular in some cases, but especially parallel, because parallel means we run in the same direction, which is always nice. So, first step here, I need to actually get the u vector, which is the direction of travel. Okay, now because it's parallel, I just need to read off from the equation that I was given what is the direction. Okay, remember your A, B, and C, which is your direction, is your denominator. So it's going to be 3, negative 2, 13. Okay, so that's the direction that line's travelling. We know the point 6, 3, negative 5 is going for a line that's also parallel to that, so it's going to have the same direction as that there. Okay, so what our equation will look like. So again, the point we're interested in is when it's 6, 3, negative 5, so that'll be my x1, y1, and z1. It did ask for the symmetric version, so it's going to be x minus x1 over A equals y minus y1 over B, which equals z minus z1 over C. Remember, this is direction that's travelling A, B, C. Okay, so therefore my answer will look like x minus 6 over 3, y minus 3 divided by negative 2, and z. Z minus z1, which will become plus 5, divided by 13, which would equal the parameter t. Okay, which again, if we wanted to parametric, we could rearrange, but that's all it asked me for there. Okay, so again, we went through a lot of examples there. Please pause the video at any point if you want to go back and read anything. But now try the exercise on the equations of the line sheet.